Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're delighted to have Ronan Colbert today, visiting us for the day. Let's see, is it NEC right now? Has been for a few years. He got his PhD and master's work with the Bengios, Montreal, University of Paris, his PhD.
Yeah, it's a bit strange.
And today we have a little slot of half an hour or so that is free, that's opened up. It's a very popular guy. So if you'd like to talk to Ronan some more, just come up after the talk. And today is going to talk about natural language processing from scratch.
Thanks for the introduction and thanks for inviting me. So indeed, I'm going to talk about natural language processing in a quite unusual way, I would say. And this is joint work with my ex-office mate Jason Weston, who is now at Google, Leon Botou, Corey and Pavel, who were interns at NEC. So, I mean, before I start, I prefer to say why we got interested in natural language processing, even if it sounds a bit crazy. Hello. Basically, we wanted to have a conversation with our computer. I mean, it sounds, of course, crazy. I mean, if you want a less crazy goal, you can say that you want first to convert a piece of English in like some computer-friendly data structure that would, keep the semantic of English. So that's really towards this goal that we are going. And well, of course, natural language processing is a good, stepping stone. So that's why we got interested in natural language processing, to at least, know if the computer understands something by using natural language processing benchmarks to measure if it works or not. So natural language processing has been, existing for a while, of course. So there are a lot of tasks existing out there, and I'm going to get interested in just a few tasks today. Some are really easy, like part-of-speech tagging. It's just like a syntactic task, which is about trying to know if a word is like a noun, an adverb, an adjective, and so on. Then you have like chunking, slightly harder. It's a bit syntactic as well, but this time you want to get syntactic constituents. So, where are the noun phrases, the verb phrases, and so on. Then you have something a bit semantic, which is called name entity recognition. You want to know if a word, or like a chunk of words actually, is like a person name, a company name, location name, and so on. And something even more semantic, which is the hardest task I consider today, which is called semantic role labeling, which is about to find interactions between words. In fact, you choose a verb beforehand in the sentence. For example, in this sentence, there is only one verb, so I can choose only 8. And I want to know what is acting on 8, or on what it's acting. So John is acting on 8, obviously. It's acting on the apple. When it's acting, where, things like that. So these tasks have been around since quite a while. And, like the NLP people have been proposing a bunch of benchmarks. And the benchmarks I'm going to consider here are based on Wall Street Journal data and Reuters. So the Wall Street Journal, for the benchmark I'm interested in, consider up to 1 million labeled words. And for Reuters, it's about 20K labeled words. So the setup we considered is coming from the ConLL competitions, ConLL challenges. So ConL 2000 for chunking, 2003 for NER, and 2005 for semantic role labeling. And the setup we consider for part-of-speech is exactly the same. And many people have been using Tutanova in 2003.
Why the bold?
Yeah, that's a good question. So actually, it's competitions. So when it's about challenge, people try to get the highest score at all means, and sometimes they use even external label data. Sometimes they really overtune their system. So in terms of comparison, we are I don't think it brings anything. So what we chose in bold, it's like what we will call in the rest of the talk, the benchmark systems, which are really well-established systems which don't use external data. I mean, they might use external unlabeled data, like Endo and Zhang. But except actually for this one, they don't use any external data.
The kernel competition are pretty strict about not using or using. So there are actually two sets of reports.
Yeah, I know.
And so it's always been like that. So,
yeah.
And then the test set is not available until the end, so people are not actually tuning in.
Yeah. But for example, I mean, this guy is using like, you know, some external NER.
But that was one set of
yeah, I know. I mean, I just, but I mean, what I reported here is really the top results that I could find. So, yeah, that's it. I'm just saying that in bold, it's like the well-established system. We don't use any external data for comparison purposes. So, yeah, natural language processing tasks are in general, I mean, quite complicated tasks. And if you have a complicated task, for me, you need a complicated system to solve it. And I see two extreme choices to do it. I mean, the first one that I call large-scale engineering is that you handcraft a lot of, you know, good features. You know that it's good features for your problem. And you feed all these good features to your system, like a basic linear model or whatever. I mean, the support vector machine works fine. And actually, a lot of natural language processing systems that I've seen work like that. I mean, in fact, my father is like a machine learner. So when I was young, he told me about, you know, Minsky on paper and the limitation of a linear algorithm. So I never really could like this kind of method. And instead, I'm more on the extreme side, which is what I call large-scale machine learning. Instead, you use like, you know, the natural features that you have for your problem. In our case, it's like straight text, just words. And you feed these features to a complicated system. So instead, you need to handle a complicated system, which will implicitly learn the right features which are relevant for your task. So in the talks, that's really in this direction that I'm going. Yeah, so just like to say a bit of what, you know, these top systems that I've been citing, I mean, usually they really like choose some good handcrafted features. So in the case of like tasks like part of speech or chunking, it's actually not that bad. I mean, here I went a bit crazy, but it's usually just a combination like of words or a combination of words on labels. Like, you know, it's not that bad. But when it gets to more complicated tasks like semantic or labeling, I mean, it might be really complicated features. And you feed like these features to a shallow classifier like a support vector machine. In fact, often what they do is that they cascade features. So for semantic or labeling again, they would like first handcraft some features. From these handcrafted features, they would feed that to a classifier, which would produce part of speech tags. Then from these part of speech tags, you would like build a parse tree. And then from this parse tree, you would like again handcraft features from this parse tree, feed that to another classifier, and finally, you know, obtain the tags you are interested in. So that's what they are doing. I mean, it works very well, but in our opinion, it really limits the natural language processing scope, because each time you have a new task, and actually if the task gets harder and harder, you have each time to like find again some new complicated features. So we didn't want to do that. We wanted to like, you know, try something else completely different. And instead, we would like, you know, to find some good unified hidden representation of like words, of like, you know, a piece of text in English. And like this hidden representation would allow us like to build a kind of unified natural language processing architecture which would like work easily, or I mean, which would be easy to adapt on all NLP tasks, at least NLP tasks which involve tagging in the first step. So the means we use to go in this direction are, first we start from scratch. So we forget about everything that they have been done until now, The only thing that we keep is that we keep the natural language processing benchmarks, which are still very interesting data for us because we need to compare our system against the rest. But really, our dogma in this work is like, avoid task-specific engineering. So we need like a system which basically scale well, because we need like to train about on millions of examples, and also we need a system like which is able to get automatically hidden representation. So it occurred to me that the most obvious system was like neural networks. So I'm going to talk about neural networks. You maybe all know about neural networks. For me, a neural network is just like a theory of like matrix vector multiplication followed by some non-linearity. In our case, we use this hard version of the hyperbolic tangent, but you can use whatever you want. So these neural networks are trained by, how to say, what we call weights in each matrix vector operation, so are trained through a process which is called usually backpropagation. And basically you get like an increasing level of abstraction in each layer. I mean, you can just feed your data, like straight words somehow. And in all the layers you are going to get an increasing level of abstraction. The only problem is that how to feed words, because, they just understand vectors. So, how to feed words to these neural networks. So, in fact, it's quite easy. You just like embed directly words into a vector space. So what I'm saying right now is actually quite old stuff. First of all, neural networks is old stuff. And then this embedding idea is also old stuff, like Yoshua Bengio used it in like 2001 for some language model. So yeah, a word is just a vector. So, but these vectors are going to be trained. So I really insist on that. It's trained by backpropagation. So yeah, because I really, get always questions like, how do you get this feature vector? Well, I train them, so it's trained. So the implementation is like really just a lookup table. You have like a big, huge matrix actually, which is about the feature size you want for your words. In my case, it was 50, if you want to know. And times the dictionary size. In my case, it was at the beginning 100,000, so it's quite huge. And the lookup table just returns you for a word, which is basically an index in a dictionary, a column of this matrix. That's it. So once you got this idea, it's very simple. The simplest architecture you can do is, okay, suppose you have like the sentence, the cat sat on the mat, and you want to tag the word on. You just take a window of text around the word on. For all words in this window of text, well, you have your features. In our case, it's basically words, but you could have also, stems if you like, or whatever. If you want to use some tags coming from I don't know where. So you have all your features. You apply like the lookup table idea for all these actually discrete features. And so for all words, you like get a bunch of vectors. You concatenate everything, and you just feed that to classical layers of a neural network. That's it, nothing else. Everything is trained, as I said, by backpropagation. So by doing that, you tag one word at a time, so you have to do the same thing for all one in the sentence. And well, actually, it works fine for most tasks. So like a part of speech, name entity recognition or chunking works fine. But when it comes like to tasks which like require long-range dependencies, like semantic relabeling, in semantic relabeling, you remember you have to choose a word beforehand, and then you tag words in the sentence according to this, a verb beforehand, and then you tag words in this sentence according to this verb you chose beforehand. So the verb might be even like outside the window, so you cannot really use this method in that kind of case. In fact, in that kind of case, you have to fit the complete sentence. The problem is that, you know, sentences vary in length. So you have to adapt a bit this architecture. And
What's happening in the second box? If the first box is generating these fixed length feature vectors for each word,
this one?
the one above, so you've got K weights for cat.
Sorry, actually, these ones are just like numbers. I mean, just integers.
Oh, okay.
So I mean, it's like an index in a dictionary in each time. Yeah. So you have like dictionary of features. For example, you have like a dictionary of words, a dictionary of stems. So it's just that.
So if you cascade descent and you start your lookup tables, you look the weight 0. Yeah.
Random.
Oh, random.
Yeah.
Okay, because you won't move the rare words very far away.
No,
from the initial.
exactly.
That's okay.
There is a problem there indeed, that we'll solve later. But there is a problem with rare words, obviously. Yes. So when it comes to like feeding the complete sentence, there is another classical, system. I mean, classical neural network approach, which is called convolutional neural nets. I mean, it's the obvious choice if you are dealing with sequences. So in that case, we are going to feed the complete sentence, and as we are going to tag one word at a time again, with respect to one verb at a time, we feed additional features, which just like are position features, which basically say to the network, hey, I want to tag this word with respect to this verb. So convolutions are basically a generalization of this window approach that I just described before. You consider the complete sentence, and for all window of words in this sentence, you concatenate like the window of vectors. You apply a matrix vector multiplication. It gives you a local feature vector, and then you shift. You do the same operation. Okay. So you are going to do that for all window of text in the sentence. It gives you obviously like a number of local features, local feature vector, which is dependent on the number of words in the sentence, right? So you still cannot fit that directly to a classical layer of a neural network. By the way, if you like, you can stack several of these convolutions. It's quite classical. In my case, I just needed one. So once you've got these local feature vectors, you remove basically this time dimension that is annoying by applying, for example, an average or a max or something like that, right? In my case, I use the max to try to extract the most interesting features, but you could have used an average in other situations or weighted average or whatever. So you really compute the max for all features, and it gives you like a fixed size vector, which really represents globally the sentence. And you can feed this vector to classical layers. So in the end,
So what max, that means you choose only a subset of features. So after convolution, you get everything. Is it?
yeah, for example, the convolution will produce you like local features vector, which are like a size 300 here. So you have 300 numbers, and times basically the number of words in the sentence. So you just max. Yeah, I chose the max. Actually, I tried with the softmax, but yeah.
Okay.
So once you've done the max, your representation of the sentence is a sort of bag of temporal features.
Yeah.
Each has a little bit of temporal structure.
Exactly, yeah.
And you don't know where it is.
I know because I included, yeah. I included the position feature as well. So I know.
So how do you represent position within a sentence when you've got variable in sentences?
So actually it's a discrete feature, right? It's just something which says I'm like 3 words away from the word of interest, for example.
Relative to the word of
Yeah, it's relative to the word of interest. So, and then you have the lookup table, which computes whatever you want. So the network looks like that in that kind of case. I mean, you have the complete sentence here, your features again, which include this time the position features for the word and the verb, for example. And then the convolution, the max over time, and then classical linear layers. That's it. So we need to train this beast. And well, we are in machine learning, so we are given a training set, right? And here what we did is that we interpreted the network outputs into like some probabilities. So I will show you later 2 ways of doing it. But let's just first like talk about how we train it. And then we just like maximize the log likelihood. So very simple. We use stochastic gradient ascent, sorry. And you know, people say sometimes, oh my God, it's complicated, it's non-convex, there are many layers. How I'm going to train that? We didn't use any particular tricks. I mean, actually I use a fixed learning rate, and I just divide the learning rate by what we call the fan-in. And also the initialization is according to the fan-in, but there is nothing else. So you can do it at home. And the backpropagation, I mean, you probably know that it's just like, you know, chain rule. So you have this modular approach. Each module basically computes its gradient with respect to its own parameters, but also with respect to its inputs.
So how did you initialize the level?
Randomly, according to the fan-in.
Okay. All layers.
Yeah.
Oh, okay.
So isn't that true that backprop doesn't usually work very well for deep networks? More than about 2 or 3 layers.
Yeah, some people say that because
This is not that deep.
yeah, it's not that deep first. In fact, yeah, there is only, you know, two or 3 layers. I mean, actually for the semantic labeling, there's 3 of them, but it's not that deep. It's true. I mean, you have this exponential decrease, so it might be a problem. Jeff.
Is it the case that most of your parameters are in the feature vectors for the words?
Sorry?
Are the majority of your parameters the feature vectors for the words?
Yeah, exactly. And that's going to.
On each iteration of learning, you don't touch most of the parameters.
Yeah. But it's efficiently done with the lookup table. So the question now is how to interpret this neural network outputs into probabilities. So the first classical, way of doing it is just apply a softmax on the output, and that's it. So you know about softmax, yeah? I mean, you just like take the exponential and you normalize with respect to all the other classes. So you basically get a conditional log, probability. If I take the log, then it gives me a conditional log log probability. I'm using here the logad addition, the logad operation, which basically gives me this score. And you can see that basically you are pushing up the score of the right class while pushing down all the other ones. Okay. You can see the logad if you want as a kind of, it's actually a softmax. So at the extreme, you are basically pushing down only, the top score. The only problem of this criterion is that it doesn't take into account the sentence structure. It's just like word per word. So instead, we can actually take the sentence into account. We can look at the complete sentence, and for all words in the sentence, I'm going to ask the network to give me, scores for all tags in my problems. So I have, for all words, I have like these tags, and I'm going to consider actually an extra score for jumping from one label to another one. So I have basically a transition score. So the global score I'm considering over like a sentence X with like T words for a pass of tags I is basically the sum of the score outputted by the network along this path plus the transition scores. And as before, I can just, apply the softmax idea, this time with respect to all the paths. and I get like a likelihood. The only problem is that I get this logad, which is over all the paths, right? So if I do it like, in very naive manner, I have quite, too much terms. But, of course, there is classical algorithm, which is like called, which is called the forward algorithm to do that. So, this slide was just to say that basically, once again, here you push up the right path and you push down all the other paths. So the forward algorithm is just like a way of computing this logad over all paths in a recursive manner. You suppose that you were able to compute the logad over all paths up to the word t-1. And knowing that, you can easily compute the logad over, up to the word t with that respect. Whatever. So the training is, again, backpropagation, and you can actually backpropagate through this recursion. It's just applying the chain rule as usual, as any other module. So it's quite simple as well. I don't detail the derivation, which is a bit annoying, but it's really just the chain rule. So this idea actually is also very old. It's a particular case of like graph transformer networks proposed by Léon Bottou in 1997. Ah, okay. I will tell him.
Sorry, I tell that to
I didn't know actually.
Well, the French encoded is different from.
Yeah, exactly. I have this bias, so obviously. Yeah, so it's old. Not saying that I'm young, but whatever. So, and also later, it has been used actually quite extensively with like conditional random fields. Conditional random fields is just like this approach where the network is basically linear. It's nothing else. Okay. So, yeah, so that's it. We train by backpropagation, and that's it. The inference, at testing time is just like the Viterbi algorithm. So you, in the forward algorithm, is basically replacing the logad by a max. But that's all. So we applied these two, these two networks, like convolutional or window approach, with the two criterions, like the word likelihood or the sentence likelihood. Just like that, straight out of the box on like all the tasks. And here are the results on all the tasks. In part of speech, it's like per word accuracy. The other one is like F1 score. And you can see that it doesn't work that well. Actually, it's not that bad. It's like in the, if you look at all systems out there, we are in the middle somewhere, but we are quite far from the state of the art. The sentence likelihood helps a bit, but still, we are far. So, if you think about it, it's not that surprising because the capacity of our network is like really mainly in the words, as you were saying. So, Jeff was saying that as well. So, the question is, are we training it right? So if you think about it, if I have a sentence like the cat sat on the mat, and then another one, the feline sat on the mat, feline is a rare word, but it should still get the same kind of tags than the cat sat on the mat for all the tasks I'm talking about, because semantically the same. So if I look at the embeddings of the network, yeah, I took like random words in the dictionary. Underneath here, like the number is like the rank in frequency of the word. So high rank means it's very rare, and low rank means it's quite common. And I look at, in the embedding space, the 10 closest word according to just the Euclidean distance. So obviously, it doesn't seem to get anything, at least according to this distance. So you might argue about it, but doesn't seem to get anything. And it's really not surprising because there is about like 1 million of words in Wall Street Journal, but 15% of the most frequent words appear like 90% of the time. So many words appear only like few times, like 10 times, 5 times, 2 times. So I mean, you cannot expect to train a 50-dimensional vector with that. So we had to do something, and we decided, let's try to leverage all this unlabeled data that we have around. I mean, just take the web. I don't know how many hard drives you have in the basement here, but there is a lot of unlabeled data. And if we could, get the structure from this data, it would be nice. So if you have a black box which is able to answer to the question, like if a piece of text is actual English or not, then really this black box knows everything about language, right? It knows the syntax, the semantic, and everything. So we wanted to try to create this kind of black box. It's basically a kind of language model. So language model with neural nets, it's again an old idea because as I said before, Yoshua Bengio tried it in 2001. But he tried it and it didn't get any good embeddings. So we don't know why exactly, but he was actually using like a cross-entropy criterion. And the entropy criterion is really largely determined by like the most common words. So in our case, we don't really care of that. I mean, for us, like rare words are as important as common words. It's just a question of is it English or not. So instead of using this this cross-entropy criterion, we use like ranking margin cost criterion. So basically, we have this network, which is a window approach network as before, which is going to produce me a score for a piece of text. And I want the score for a true English piece of text to be larger with a certain margin than the score of the same piece of text, but where I replace the middle word by some random word. So that's what I will call the piece of text which is not English, basically. So we train that again by stochastic gradient, but we train it like on a lot of data. So we first took Wikipedia. At the time I took it, it was like 600 million of words. And then I thought it was not enough, so I found recently on my hard disk another language model I trained, I forgot about, which was also using Reuters, which is an additional 200 million of words. I mean, those kind of data sets are really massive, so you cannot expect, like I train it quickly, I see if the parameters are right, they are not, so I mean, I'm doing cross-validation or something like that. I cannot do that. So instead, it's a bit like in biology, you breed networks, you try some, you look after like 1 week, oh, it's doing well, so I'm keeping it. This one is not doing well, I'm killing it. And, or I'm, splitting several experiments or whatever. So in the end, it took quite a long time to train that. I ordered the words by frequency and tried first with a small vocabulary size and then slowly increase the vocabulary, exactly as a child would learn English, And I trained on Wikipedia 4 weeks like that. And after that, I initialized another language model using these words. I added like 30,000, the 30,000 most frequent words from Reuters to the dictionary, and I trained an additional 3 weeks with that.
So what's the structure of this thing you're training? Is it the same as the other one?
Yeah, it's a window approach.
But with the same sort of architecture?
Yeah, exactly. Yeah, I forgot to say. Obviously, I wanted to use. The idea behind it was to train these embeddings to be able to reuse them afterwards, right? So it's exactly the same architecture. It's a window approach with like 11 words and 100 or more hidden units.
Does this have the convolution with max?
No, 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 no. Just a window aperture.
So what is it that you're looking at in order to make the decision to keep or to kill off?
For the networks? Yeah, I have. I mean, I split Wikipedia. I kept on the side like 1 million of words, and I'm just testing on it sometimes and look.
Is this again for semantical labeling? Or
No. That's just for this task, just for the language model task. Yeah. So I trained basically the language model like during 4 weeks and then 3 weeks on the side like that, without thinking about the other task.
So the breeding is just increasing gradually, the training set size.
Yeah.
Breeding out the bad
Yeah,
stuff.
basically it's that.
And that's happened in the second one and on the two also?
No, actually, this one I forgot about it. Actually, I let it train and I forgot that I had it. It's only recently that I rediscovered it. So, yeah. So here are the embeddings that it gets, and as you can see, it's much better than before. So you can just take these embeddings, initialize your networks with that, and do the same procedure than before and see what you get. And that's what we have here. So again, the benchmark system, our system as before without language model, and then with the first language model and the second one. And you can see that, I mean, we are really close, if not as good as the state of the art on most tasks, except maybe semantic role labeling, which is still far. The number is in italic, it's because it's still training, actually. It's the results from this morning. So I actually restarted recently because for several reasons. So, I mean, you can see that you get a huge boost from language models. And yeah, I reported here, I mean, you get really a huge boost with the second language model for name entity recognition. One reason is that the coverage is really, I mean, proportionally better with the second language model compared to the other ones. Okay. Yeah, so we still wonder, I mean, can we improve that a bit more? Because we have now this kind of unified representation of words, which seems to work very well for any kind of task. So why not, training everything together? So that's what you did quickly, just, do joint training and by sharing parameters. So basically you have several tasks and you decide, this task might actually receive like different data while you train. It doesn't matter, but the parameters are going to be the same all the time, right? You just share parameters. And we shared here like the lookup table and the first layer, okay? And I trained together like the part of speech, the chunking on the name entity recognition. You might wonder why I didn't add the semantic role labeling, but I mean, semantic role labeling takes actually quite a long time to train, so I didn't do it. Yeah, and you can see that you get a boost mainly for like chunking. I mean, linguists would tell you that it's not surprising because often they use like part of speech as a good feature for chunking. So yeah, so that was it. I mean, that was the almost from scratch part. I mean, then of course there is a temptation. We are tempted to do as other people do. Should I plug this with that and see what happens, because I know that part of speech is good for chunking, so why not plug in it? So that's what we did in this part. So we like fed some stems to the part of speech as additional features. Actually, we just like took the 2 last characters of words as features. That's it. I mean, I tried actually with others, but it was not helping. It was 2 was enough. For name entity recognition, we use like gazetteers. Actually, the CONLL competition comes with 8,000 locations, person names, and so on. So we just like are feeding additional features which like tell if the word is in one of these gazetteers. Then we use a part of speech feature as a feature for chunking or NER. And finally, yeah, I mean, chunking is often used for semantic role labeling as well, so we just like fed it to see what's going on. And it works actually quite well. For I mean, we get a boost everywhere. So this one is going to be much better. I mean, I started it a bit later, so it's lagging a bit behind, but I'm going to get a better boost than that. For the rest, I mean, you can see that we are basically state of the art everywhere. So for semantic role labeling, it still sucks a bit. In fact, for semantic role labeling, people, yeah, okay, I had this extra slide, I don't know if you're interested, but I often have the question, I mean, this is non-convex, I mean, are you scared about local minimum or things like that? So I just like train 10 times the same network to see what's going on. And I report here like the worst results that I got and the best results. So you can see there is a little bit of variance, but not that much. And in a previous experience, I always use the same seed in all networks, so it decreases a bit the variance. So yeah, as I said, for semantic role labeling, people are often saying that parsing is really essential. There are even papers about it. And the state-of-the-art system that I'm comparing against, actually, the one from Kuman, Punyakanok, and so on, they are using like 6 parse trees. Like they are taking the Charnak parse tree and they like just, you know, take the, actually, twice. Them they use like five parse trees. They take the first top 5 parse trees returned by the Charnak parser. But I think another one, the third best system, use like 6 parse trees. They use also the Collins parser. So, I mean, we thought, I mean, why not, you know, trying to fit these parse trees as well somehow. So what I did is that I took the parse tree and take the last, how to say that, I mean, the tags at the last leaves of the parse tree, right? And then I mean, so that gives me like, you know, basically chunk tags. I mean, chunk tags, but where what is called the bracketing, I mean, where it starts or where it ends are slightly different than chunking. But other than that, the tags themselves are really chunk tags. Then I mean, then I remove the extreme nodes, and it gives me basically the next depth of the parse tree and so on, right? And I try to feed up to like 5 levels of the parse tree, and it's actually working pretty well. So it's still trying again, but I mean, we get like really good results. And actually, if we compare against the system of Kuman, Punyakanok, so which is really the best system for semantic role labeling, they report one result with only the top Charnak parse tree. It's a result on like the validation set, but still, and you can see that we are really in the ballpark of the results. But we have a big advantage, is that our system is like really pretty, you know, standalone, simple. I actually took all the results, and I produced like a simple implementation in like C. It's like just like 2,000 something lines of code. Neural networks like perform mainly matrix vector operations. I can use BLAST to go even faster. And basically, I mean, to summarize, all networks are like given like low caps words. And yeah, maybe I forgot to mention that actually. I fed only like lowercase words, but as I lowercase the words, I kept the capital features not to lose any information. So the part of speech use also like this, actually it's suffix, I don't know why I put prefix. Chunking use like a part of speech tag, name entity recognizer use a gazetteer, semantic role labeling use like the first level of the parse tree that actually we predict with another additional network, which predicts the last level of the parse tree in a better way actually than the Charniak parser. And also train like an additional network to predict verbs as in semantic role labeling. I mean, they have a particular way of, taking verbs. For example, if I say, I don't know, Microsoft is going to buy Google tomorrow, is and going is like two verbs according to part of speech, but they are considering only going. So just a little detail. And as you, okay, my slides are a bit, somebody randomized them, I don't know. Okay, yeah. So it's going extremely fast. That's what I wanted to say that. I compared against like top systems which are out there. Actually, there are not many. So for part of speech, there is the best tagger from Shen in 2007 and Tutanova. And you can see that we are ridiculously faster, and we need really like a few memory compared to them.
Is the evaluation?
Yeah. No, is that the evaluation? Yeah, the training, it's another story. It's yeah, that's for the part of speech test set actually.
This is a research system. So I have a part of speech tagger that does similar to Tutanova, and it does 50,000 sentences a second. 42 seconds.
Yeah. I don't know. So actually, the system is going to be available like in mid-January, so you can compare. The problem is that I have no system out there. I mean, I took what I have. So if you have one, you can tell me. I'm fine with it. I was honestly surprised by the part of speech one. I didn't expect that because, I mean, it's just, features on a linear model and a decoder that they put on top and not much. So I don't know. For the semantic role labeling, it's less surprising because they need to compute all these parse trees, which is quite expensive. So again, it's really fast. So I have this, demo if you like, because you are a software company. So it's just like, few lines of C code. And the compilation is pretty, I mean, it's really standalone software, right? So I just want to use BLAST, so I had this thing. I'm sorry, I'm using an Apple computer, but it works well anyways. And that's it. I mean, if you have a good sentence in mind, otherwise I will come up with one.
Colorless green ideas sleep furiously.
Chelsea.
Exactly.
So you say colorless?
Colorless green
ideas. Sleep famously.
sleep
Furiously.
furiously.
So I'm afraid it's a bit far from the whole speech journal data, but whatever. So you get the tag instantaneously. And I don't know if you like it or not.
So A0, so it's saying that's the argument 0 of sleep.
Yeah.
The manner. It looks fine.
Yeah.
Yeah, but these things are balanced. What's the lexical ambiguity of these things? 0. I mean, colorless cannot be an issue.
Sure. No, you
So,
Do you have one, Christina? Give it a hard sentence.
So I'd be interested in seeing passive construction. So Christina, what are the ones, some of the passives that are a bit hard?
Flying planes can be dangerous. Flying planes can be dangerous. Flies like
Yes, territory flies like an arrow. Great. This is a tough crowd. Oh. Yeah.
Yeah, so in fact, I mean, it's probably correct, but you have to look at the frame, because I mean, if I look at the arguments or whatever, You have to look at the frame of the verb, because depending on the verb, the arg0 and the arg1 means something different or something. So they have like this set of frames which defines for each verb what is arg1 or arg0 or whatever. So.
Although flying is not shouldn't be the verb here.
It is a verb, but this is correct. The B has
It's a generic.
Yeah, so the B is because strangely,
Okay, sorry.
yeah.
I think the intention. But now, there really are two predicates in this structure following the standard Rockback annotation, right? So what do you do when a sentence contains more than
What do you
one?
mean by two predicates?
So there's a flying planes,
Yeah.
some action that occurs.
Ah, yeah.
And then it's in turn the subject argument or the nominative
No,
argument
it was too low.
at copula B.
Yeah.
So you only identify the first predicate or the most likely predicate or the max predicate?
No, you mean like for flying on a B, you say?
Yeah.
Yeah, so actually, bizarrely, in the so that's when I said I have these networks which like predict verbs according to the semantic role labeling dataset. Bizarrely, I don't know why, many of the verb be or actually have, they are ignored, they are not labeled. I don't know why. So the network trained to not label them as well. But I mean, I have this option that I didn't implement yet, where you can consider a part of speech verbs instead, and so you get all the verbs then. So.
How about fruit flies like banana?
Fruit flies.
Fruit flies. Space.
You know, deliberately ambiguous.
No,
Flies.
fruit flies like banana.
Like that?
Like a banana. That's what introduction of fruit doesn't fly like banana.
Yeah. So whatever. I mean.
But if you have the cat was chased by a dog,
That's
By a dog, you say?
Oh,
Ah, see.
so that you do get the passive correct.
Yeah. No, I mean, it's working. I mean, you saw the F1 score is pretty high, so it's working well. So I had other sentences. I don't remember what it was, but yeah. So that was to show, for example, it gets very well organizations. But anyways. So yeah. That was just to say basically that it's really, a standalone software, very small, and it works very well and very fast. And that's the conclusion. I mean, I presented you like a quite all-purpose neural network architecture for natural language processing, which really limit like a task-specific engineering by instead like trying to rely on very large unlabeled data sets. So, I mean, of course, we do not plan to stop here. For us, it's just, the beginning. We got like this good hidden representation for words, but now we are more interested in good hidden representation of like piece of text. So we've got some critics from that, like, why forgetting natural language processing expertise, like for, trading it for neural network training skills. And what I mean, our argument is that NLP goals are not limited to existing natural language processing tasks. And if you get like some new task, which might be more complicated, you might not want each time, to find the right features. So we don't think that excessive task-specific engineering is desirable. And also I got like some people, some actually very well known, telling me, why neural networks have been obsoleted 20 years ago. So, well, it scales on massive data set, as you saw. We were able to discover some very nice hidden representation. And also, it's well proven. All the technology I've been using almost existed in 1997. The only thing is that it was really the right time to do that. Because if we had started in 97 with like vintage computers, we will be probably still training right now. So that's it.
to continue on with the question that Chris had, where you have, if you have the flying planes can be dangerous. So let's just say in the symmetrical labeling task, you would be required to know that flying planes was the subject, or had an argument role with respect to be dangerous. So can you handle nested events like that? I'm working on biomedical tests right now where you have the phosphorylation of some gene inhibits some other event. So you have massive nesting of these labels with respect to each other.
Yeah, I mean, here there's not much nesting, obviously. Yeah, so yeah. Well, I mean, I'm interested in more nesting. Actually, the work I'm doing right now is like the next step, but I cannot talk about it. I'm sorry. Yeah, I mean, taking just this work like that, it's not enough for what you want to do. You need, to go really like to try to represent piece of text and find nice way to represent them, but it's.
So the algorithms here don't working with
No, you need some more complicated networks, basically. So, sorry.
Have you tried anything in other languages?
Other languages? Yeah, actually, NEC is a Japanese company, so they are quite happy to try that on Japanese. And also they are very involved like in trying to get on the Chinese market, so we tried on Japanese, Chinese, German, and it works. That's all I can say. Yeah.
So maybe more of a comment than a question, but it seems like what you have here is a really fascinating way to leverage unsupervised data.
Yeah.
In the supervised case, I can take a simple maximum entropy model and just look at character prefixes and suffixes on the English case and do better than what you did on the part-of-speech tagging accuracy.
Yeah.
Yeah. So I mean.
But I mean, the question is, I mean.
All I do is take all
no, but
four.
The thing, I mean, that's the philosophy is different. I mean, the philosophy is different. I mean, what we want here is a general architecture which works for all tasks. What you described doesn't work for all tasks. So, in my opinion, we get more if we try to find something really generic which works for all tasks, because we are really trying to go in the direction, trying to, get representation of English. So that's really the direction. Other than that, I'm not criticizing. I mean, I know it works. I mean, I know you can do it, but.
And so the other thing is, it feels like some of your comparisons are really quite unfair. Because on one hand, you have like 1 million words of training data, on the other hand, you have.
It's true,
billion,
yeah. It's true, but it's unlabeled. So. Yeah.
But if you took that same unlabeled data and threw it into.
Maybe actually, Ando and Zhang actually are the only one which are really using well unlabeled data, and it works very well. So. I don't know. Maybe I don't. They didn't do it, so I cannot compare. So. Yeah.
It could be very powerful.
Yeah.
The only thing I'll say about your last slide here is you say why forgetting NLP expertise. In fact, you haven't forgotten NLP expertise.
No, I know.
It's just that you've used the very painstakingly, laboriously produced.
Yeah, I know,
and so
for
it's
sure.
not forgetting,
But
it's just a different encoding.
Yeah, exactly. We recognize that. But I mean, that was in the section critics that some people told me that. So I'm just like repeating what they told me. But
Very much, but
yeah.
in the same way, you could criticize this algorithm as well, this methodology as well, because without a training set, you can't do it from scratch. Right? What can you do from, I mean,
well, you can
it's
do
not from scratch as such.
It's not exactly true to my opinion.
Okay.
Because I don't want to stop on natural language processing task. I'm not a linguist. I'm not particularly interested. So, but what I really wanted is like trying to get good representation of English. But the question is, how do I know that it's good representation? So for me, I use natural language processing benchmarks just to show that look, it works on all your benchmark. So it must mean something. I mean, it must mean I learned something. That's all.
But so say you have a next task that you want to solve for natural language processing in order to accomplish some result. if there's no benchmark, how would you approach?
If there's a next task?
If there's no benchmark.
Yeah, but that's the
So
thing.
say I want to know what the location is of every noun
Yeah. Well, I mean,
I extracted from text. There's no benchmark for that.
yeah, but that's the thing. I mean, it's not my goal. My goal is really not trying to solve all NLP tasks. So I'm using just NLP as a way to benchmark what I want to do. That's all. And what I want to do is get
No, I
good.
think the point that she's
Yeah.
making is that because you're showing good results on some
Yeah.
of these tasks, you imply that any other task that you do
Ah.
will have similarly good results. And without a benchmark,
Yeah,
you're not
of
sure to whether
course, but
that's
I'm not
right.
interested in trying all NLP tasks.
Is that what you're saying? No?
So, but the point here is, have you tried to use, for example, train on Wall Street Journal and test on brown corpus? And if now you get good results on the other corpus, you can say, oh, I'm leveraging all this data and I'm getting good results.
So actually,
If you train on Wall Street Journal, test on Wall Street Journal, it's not more, it's just another system of doing this task. And it's a general enough system that can accomplish it, right?
Maybe a better thing to say is if you had,
by the way, the semantic
Training.
quality. Wait.
so you have a notion, there's a training notion, because you have to output part of speech tags.
Yeah, but that's the thing. I don't have. That's what I'm saying. It's not my goal. My goal is, just find good representation of English. So, but that's it. That's all I want. And then I'm just saying, use, how good are my representation? I have no idea. But one way to find out is trying many natural language processing tasks and see if it works fine or not. So that's just what I tried.
I'm sorry.
When you say good representation of English, do you mean good feature vectors for words?
Well, that was the first step here, but of course, I would like good representation of a piece of text.
Right, but what you're trying to, all the results you showed are basically showing that
Yeah.
you've got representation, feature vectors for words
Yeah.
that are useful for all these tasks.
Yeah.
And therefore, presumably, good.
Exactly.
That's what you claim to establish.
Exactly. I don't claim anything else.
And you never said how big the feature vectors are. How many components?
Yeah, it was mentioned in the slides, but it's 50. Yeah. Actually, yeah.
Did you try different sizes?
Yeah.
And 50 was better than 100?
No. But no, in fact, I tried different sizes, like on this natural language processing task, and it didn't matter much.
Unsupervised pre-training.
Sorry?
With the unsupervised pre-training,
Yeah.
than the ones with PD, you'd expect the ones to do better.
It didn't change much, basically. But if you consider just a language model task, for example, 100 is much better than the 50-dimensional one. But I didn't report here any results on the language model because I cannot really compare against any other language model as I have this ranking criterion. Usually people, report results in like perplexity or something else.
You can evaluate in machine translation. Have the scoring function.
No, not like that.
All right, let's speak one more time.